Hello and welcome to Factually. I'm Adam Conover. Thank you so much for joining me once again as I talk to an incredible expert about all the amazing stuff that they know that I don't know and that you might not know. Both of our minds are going to get blown together and we're going to have a ton of fun doing it. Now, this week, we're talking about one of the most incredible scientific breakthroughs of human history. See, scientific progress doesn't happen in a linear manner. For every breakthrough, there are 1 million dead ends and 100,000 mediocre papers that nobody ever reads. It's all fits and starts, and many more fits than starts for that matter. Decades can go by with very little progress, and then all of a sudden, boom. We go from studying electricity to using it to power our houses. We go from looking at the moon to landing there. There are these turning points in science that transform human society so profoundly, we suddenly can't even imagine what life was like before them. The moments that science goes from explaining something to being able to manipulate it. Well, as our guest today argues in a new audiobook, we are in the middle of one of those transitions right now. Remember those mRNA vaccines that came out of nowhere to save our ass during the pandemic? That vax that's likely coursing through your veins right now? Well, those are just the tip of the scienceberg, because suddenly it seems that we have new tools to futz around and hack life itself. And these tools work. Foundational biological properties can now be manipulated in ways that would have been unimaginable just decades ago. Nearly 4 centuries after Robert Hooke became the first person to observe a cell under the microscope, we have arrived at an incredible moment. Humans now have the power to dominate and control the cell itself. This new world of synthetic biology brings tremendous opportunities for medicine, climate change, agriculture, and so many other fields. But it also brings along with it a lot of new dangers and a lot of things we should really be worried about. Our guest today argues that these advances will create something like a new industrial revolution. And we all know how that turned out, for better and for worse. So this is an incredibly important, fascinating topic, and I'm so excited to jump into it with you today. But first, I want to thank everybody who supports this show on Patreon. If you want to support, head to patreon.com/Adam Conover. Just $5 a month gets you every episode of this podcast ad-free and so much more. And by the way, come see me on tour this year. I'm doing my new hour of stand-up all across the country. From March 23rd through 25th, I'll be in Austin, Texas. From May 5th and 6th, I'll be in San Francisco, California. On May 11th through 13th, I'll be in San Antonio, Texas. And June 8th through 10th, I'll be in Batavia, Illinois, just outside Chicago. Head to adamconover.net for tickets. That's adamconover.net. And now let's get to our interview. My guest today is New Yorker staff writer Michael Specter. He has been covering science and the breakthroughs that are just around the corner for literal decades, and he is such a fascinating writer and speaker. I'm thrilled to have him on the show. He is the author of the new audiobook, Higher Animals, Vaccines, Synthetic Biology, and the Future of Life. Please welcome Michael Specter. Michael, thank you so much for being on the show.
Oh, it's my pleasure.
So tell me, what is synthetic biology, and why do you think it's the next industrial revolution?
Synthetic biology is the ability to manipulate the basic elements of biological life in synthetic ways, by making elements, by making parts of cells, by making DNA, by making amino acids and putting them together. I think it's the next revolution because we've already seen what it can do. I mean, one very obvious example is the mRNA vaccine that has been administered about 14 billion times so far since the beginning of the pandemic.
Yeah.
That was a vaccine. Both those mRNA vaccines were downloaded from the internet. The blueprints were printed. They were posted on the internet, downloaded all over the world. Scientists then put the DNA together, infected cells, and within a few days, they had recreated the virus. And that was why Moderna had the vaccine that essentially is used now within 5 days.
Yeah.
So, yes. So the ability to manipulate these basic elements of life in a lab, which seems a little Frankensteinian when you say it in those terms, is really very powerful and exciting. And yeah, it also has some downsides, which I'm sure we'll discuss. There are all sorts of medical solutions that synthetic biology will be able to provide. But synthetic biology can also do many other things, including industrial issues, chemical waste, biological waste, species. It's something that can really help with conservation. There's no end. We're talking about biology. We're talking about reproducing biology. Biology basically does everything pretty well. So and we're nowhere near getting to the point where we are as good as biology, but we're getting a lot better than we used to be.
Well, there's a lot to get into there, but let's start with the mRNA vaccine briefly, because I think it's such an illustrative example. I've talked on this show before about how incredible the mRNA vaccines are. And, in terms of being a world historical scientific innovation that is like, I don't know, it's up there with the moon landing. I feel like in a lot of ways that we learned my understanding is, here's my dumb version, is that, normally to have an immune response to something, your body needs to encounter the virus. But what do you do if you want to vaccinate somebody against a virus they've never encountered? Well, we used to give them little dead pieces of the virus, but there are disadvantages to doing that. Instead, we figured out how to program our body itself to manufacture a little neutral piece of the virus that can't hurt you, basically just a little residue or a fingerprint of it. And that's what the vaccine does. It sort of like hijacks our own body's system of making molecules very briefly and uses it to knit together this exact little piece of virus that we want to tell the body about. And it worked. And like it reminded me of hacking in a way that it felt we understand our own cellular mechanisms so completely that we can just say, let's just write a little bit of code to make this one little thing that we need. Am I getting it right?
That was very far from a dumb version. There are lots of things that you brought up. The hacking thing is important because to me, what is happening here is biology is becoming part of information technology. It's digital code. Instead of zeros and ones, it's A's, T's, C's, G's. Those are the basic nucleotides of DNA.
Yeah.
And we are able to send it and rewrite it and print it. There, you can order it online like you can order shoes from Zappos. You can put it together and you can make things with it. And this, to me, and I said this in the audiobook, I think the mRNA vaccines will be seen to some degree for synthetic biology what the microchip was, what the Cold War really did for the microchip, which is bring it to life. There were lots of people in the world who were afraid of GMOs and still are, and we can discuss that if you want. But whatever objections people had to the vaccine, and some still do, hundreds of millions of people stood in line to get a piece of manufactured synthetic RNA shot into their arm. Yeah. And that's because it has a purpose, and it is a purpose you can understand. And
and it saved millions of lives.
Well, in the first year, the Lancet estimated that it saved 20 million lives in the first year.
Wow.
Now, you have to understand, the fastest vaccine that has ever been developed before this was 4 years. That was the mumps. We're not at 4 years yet. So could you imagine if we didn't have any vaccine yet, how many more people would be dead and sick, how many more schools and business? I mean, it has already been, I think, an official nightmare. It would be 10 times worse.
Yeah.
So it's a really tremendously big deal that this happened.
And you made the comparison to the microchip during the Cold War, and there's other examples of innovations happening like this throughout history. Thinking about the Enigma machine during World War II that jump-started computers, to put it very, very briefly, that these sort of wartime or crisis-based innovations that were suddenly had to be pushed into production then led to an entire explosion in a sector. And the fascinating thing is the mRNA vaccine wouldn't have even been possible to make 10 years earlier, 5 years earlier, because the technology was that new. But not only was it new, we had to push it into mass production and shoot into all these people's arms. And so you think this is similar, that it's going to result in a similar blossoming now that the crisis is, we've moved on from it?
It already has. I mean, companies now are working on mRNA vaccines for all sorts of illnesses, for cancers, for autoimmune diseases. Whether they will all work or not, I'm sure they won't all work, but some will work. And the thing about an mRNA vaccine is it's easy to redo it, just the way if I write a bad paragraph and my editor yells at me, I can just rewrite it. That's very similar to what you can do when you're making one of these vaccines. So if we get a new version of a virus, we can react really quickly. And I just think that this is going to change everything. And it already has changed everything. For 200 years, we've basically taken a virus, tried either to kill it or used a little piece of a protein from it and shot it into our bodies and hoped that it would train our antibodies to protect us from the real virus. And that's worked pretty well, and sometimes it's worked astonishingly well. But it's definitely old analog technology. And to have technology where you just say, here's the spike protein that we have a problem with. Let's give you the blueprints to make something that will lasso that protein so that anytime the virus shows up, the antibodies in your body will be on alert and defend you. That's cool. I mean, that's really something.
Are there, so you mentioned cancer and other diseases. Are there any specific diseases that are like, have been very intractable that through this method we think we might soon have a breakthrough for, or no?
Well, I don't want to be, I think journalists get excited and they hype things, and I don't want to do that. But I will say this, one of the biggest problems we've had for many, many years is producing a decent influenza vaccine. Every year we get them. Every year they kind of suck. They're better than not getting them, but sometimes they're 50% at best. And 50% is a lot because influenza, and people don't often realize this, can be one of the deadliest things on earth. So what scientists have wanted to do for some time is to make one vaccine that would prevent all types of influenza. You know, if you look at the influenza virus, it looks a little bit like a broccoli stalk. There's the stalk and then there's the head. And the head keeps changing every year. And that's why we keep making these new vaccines, because we're looking at the new heads. We couldn't until recently figure out how to create an antibody response to the stalk. But now they're having a lot of progress doing that. There's some very promising research on that. And you ought to be able to do it with mRNA technology. And I don't think too long from now, we will have it may not last your life. It may be like a tetanus shot. You'd get it every 10 years, but it would work. And it would save a lot of lives, and it would be a lot better than what we have now.
Moving on from mRNA vaccines, a couple of years ago, there was a huge amount of talk about CRISPR. I haven't heard as much about it lately, but it sounds to me like it plays into this. There was a lot of talk about it being an enormous breakthrough that would lead to all sorts of things. What is the status of CRISPR? And explain to me, for those of us who don't remember, what it is.
So CRISPR is a molecule that you can program and send to any place in your genome, and it will change the DNA in that very specific place. It's sort of like a molecular scissors. Wow. And you can say, gee, I want to take this broken gene out, and I even want to swap out something better. Now, when that was first discovered, it was obviously revolutionary, and it is. There were lots of early problems with, you could do what I just said, but sometimes there would also be these off-target effects you don't want. And they've been working on that, and they've developed better and better technology. This is a toolbox, and they're getting much better versions of CRISPR and something called prime editing, which just sort of erases one of the bases of DNA rather than cutting it all out. And, you know, you're seeing treatments for sickle cell and diabetes and things that are really devastating coming online that seem to work. And that's all, you know, CRISPR is a part of synthetic biology. It's this ability to recreate biology in a lab. And we all have CRISPR in our bodies. We never knew it, but when we figured out what it did, it was revolutionary. Now we can make it, we can remake it, we can take cells and rewrite them. And it's really exciting times. And I mean, hype or not, I don't think any of this can be called anything other than a revolution.
Yeah. Wait, so something that I've never quite understood about CRISPR is I understand that it can scissor out DNA, replace, a portion of DNA or neutralize a piece of DNA, but can it do that in like already existing cells in a, like I am, organism that has been around for a couple decades, right? Like, or does it need to be done to something, you got to take the first cell and make that little scissor and then you're waiting for it to multiply. But could it, like if I have a genetic, let's say, defect of some kind, is that something that can be literally repaired when I already am made of billions of cells,
If you are living with a genetic defect in all your cells, the answer is probably not. I think the way to look at this is we have two types of cells, somatic cells and germline cells. Somatic cells are all the cells in our body.
Yeah.
So if we figure out a way, if I have kidney cancer and I'm treated for kidney cancer and I'm cured, that's great, but it doesn't mean that if I then went and had a child, that person would or would not have a greater chance of getting kidney cancer. It's not a heritable thing.
Yeah.
But what you can do, and this is very controversial, you can edit the gene line of species. And the gene line are the egg and the sperm that you pass on and fuse. And when they multiply and divide, every cell in the body has what's in those cells. So if you were to edit something out in an egg or a fetus, then every time those cells divided, the change you made would also be made. And that means you can talk about getting rid of genetic diseases that have so far been intractable. It also means you can do crazy things like change the genetics of Anopheles mosquitoes, which carry malaria.
Yeah.
And there are people very far along on doing that. And what you basically do is you just rewrite their DNA so that when they lay eggs, the eggs die. And I hasten to say this is one species of many, many species. And the only thing Anopheles seems to do is kill humans. It doesn't seem to have any other purpose than any entomologist has discovered. So these things are really promising. But when it comes to DNA editing your germline cells, it's a scary prospect. And I think you don't want to do that if you can do something else. There was a very famous instance of a Chinese scientist editing twin fetuses for HIV. Well, there are many ways to treat HIV. And to prevent it. And I don't think the first thing you want to do is go rewrite the DNA of your species when you have an easier way to do it. Yeah. But there are going to be some things you can't fix any other way. I mean, if we could get rid of Huntington's chorea, which is a deadly disease and heritable, it would be great. And I don't think very many people would object to that. Yeah. The problem is once you get into doing that and you can do it and there's the facility to do it, maybe we can make people play cello better or be taller or have blue eyes or whatever ridiculous thing you personally think. And, it is the classic slippery slope of where do you stop? Because wherever we may want to stop in America or Western Europe or anywhere else, there will be somebody who will go beyond what we think is appropriate.
Yeah. Well, I want to get into because I have a lot of fears about what you're saying, but I sort of want to save that stuff a little bit because I want to make sure we fully explore all of the positives that, maybe I don't know about yet before I start thinking about those things. So what are some of the other possibilities that are coming to light because of synthetic biology? You talked about, eradicating, using these sort of population control techniques to eradicate mosquitoes that cause malaria. That would certainly be, if one agrees that we can, that this is one species we're comfortable with going extinct or very much limiting its population, that would save millions and millions of lives. But what else can be done with synthetic biology that's just around the corner?
Well, I'll give you an example. It isn't even around the corner. I have a chapter in my book about this. The black-footed ferret is the most endangered species in the United States. Black-footed ferrets subsist on prairie dogs, and prairie dogs are susceptible to getting a version of bubonic plague that's called sylvatic plague for these animals. And there are vaccines for this, but you can't run around the entire Western Plains states vaccinating every single black-footed ferret. It's just an impossibility.
Yeah.
But what some researchers have figured out a way to do is you can take that vaccine and you can put it in the germline cells of a ferret. You can clone that ferret and it will be born with resistance to the plague. It won't need a vaccine because it will have inherited a vaccine. And that has already happened. I mean, it's experimental. The first cloned black-footed ferret. It's called Elizabeth Ann, and I am very proud to say that I interviewed that ferret, and you can listen to it in my audiobook. You don't get a chance to interview ferrets very often.
I can't wait to hear what that sounds like.
Yeah, humor aside, there are lots of species disappearing all the time.
Yeah.
And there are ways to preserve them, and some are less intrusive than this, but this is really kind of exciting, and it's just an example of what can be done. Other things that can be done.
Let me just say it raises a big issue because, you know, your first thought might be, well, if we've edited this species in some way, injected a vaccine into its gene line, released it into the wild, and then that ferret goes and mates with a bunch of other ferrets, and now there's a vaccinated population that's going to grow because these are more resistant to this horrible disease. Well, now we've altered a natural species. And, you know, wait, is that what we wanted to do when we were preserving this species? Brings me back to a conversation we had with the wonderful science writer Emma Maris about issues like these. And she pointed out that what we have to decide is, what is our value? Are we valuing wildness versus human interference? Are we valuing the existence of the species? Because the fact is, probably a lot of the species you're trying to save from this kind of pressure, the reason they're endangered is because of human activity in the first place. Talking about something like the American chestnut, you know.
First of all, we do have to very carefully consider every time we go in and mess with the genetics of any species, ours, of ferrets, of mosquitoes. It's serious business. And I think we need to take these things case by case. But I also think you have to remember that the only reason we're discussing this sort of stuff is because we're destroying the world. Yeah. And we're killing these species at crazy record numbers. And if we can figure out a way to save them, and yeah, you have to be careful about unintended consequences. But my problem with thinking about that is that people either look at biology and say, oh my God, there are all these unintended consequences, or they look at biology and say, oh, this is so cool, you're going to save everything. Obviously, it's somewhere in between. There are benefits and risks to everything. Every number has a numerator and a denominator, and we don't usually talk about them both. We talk about one. So we're going to have to be way more sophisticated about risk.
Yeah.
And that is something that's serious. When it comes to the black-footed ferret, I'd just like to say those experiments have been done in a very controlled laboratory place. They've been done with the supervision of the U.S. Fish and Wildlife Service. Tons of people are on board. This isn't just a couple crazy scientists. Yeah. We can get to what a couple crazy scientists could do at some point, and we probably should. But I think it's really important to acknowledge that we've done some incredible harm and that we have the technology to fix some of it and prevent some of it. And I think we have an absolute obligation to do that.
Yeah. Well, I have so many more questions about this, but we got to take a quick break. We'll be right back with more Michael Specter. Okay, we're back with Michael Specter. I just want to get more of an overview of what other problems synthetic biology can tackle. I understand in your audiobook, you're talking about how it can affect agriculture, affect climate change is one that I wouldn't expect. How does it?
Well, how it could is one of the biggest contributors to climate change is agriculture, and it's the synthetic chemicals we make to put on crops.
Yeah.
And you need to use pesticides if you're going to feed 8 billion to 10 billion people. But we spend so much energy and it burns so many fossil fuels. Wouldn't it be great if you could just grow fertilizer instead of make it in a giant factory? Just grow it in cells, in vats. and even implant it into its own plants. And that's what's starting to happen. There's a company that I write about called Ginkgo Bioworks that's working on this very hard. And the idea of getting rid of even some of the fertilizer that we create through giant polluting chemical factories is very exciting, and I think quite possible.
Just describe to me, like, fertilizer. Okay, I'm going to try to remember what I learned in like 10th grade, earth science class. Fertilizer, I believe the main thing is to put nitrogen back into the earth, right?
Right.
And plants suck nitrogen out of the earth as part of what they do. You need to put it back in. I'm sure there's other things it does as well. But so how would a plant have fertilizer within it, or how would it put nitrogen back in? Is there something, just describe a little bit more about it. It's fascinating.
Okay, well, first of all, plants they make nitrogen, and if there wasn't agriculture, they would just live and die and go into the earth, and then there would be natural fertilizer.
Right.
But there is agriculture. So we break that cycle. And what you find, and you particularly find it in places like sub-Saharan Africa, there's not enough nitrogen to grow the crops to feed the people. So what we've been doing is making fertilizer with nitrogen in it, and that nitrogen does help grow crops, and it causes amazing levels of pollution and destroys rivers and lakes. Yep. You can make plants to just make their own nitrogen. You can put the nitrogen, you can put the genes in the cells and grow those cells and plant those plants. And you don't have to make it in a factory. You basically brew it the way you brew beer. Wow. And that is something that I really do think is not science fiction. It's about to happen. And it can really make a big difference in all our lives.
And it would make a big difference to removing one of the most massive harms of industrial agriculture.
Yeah. And I mean, industrial agriculture is its own show and has lots of problems. But one of the biggest problems is, in order to feed so many people, we need to make a lot of food. You can't really do that in a cute, organic way like they do in the Hudson Valley, which is where I live. But you pay a real price for growing all that food. And we've destroyed so much land, so much water, so much air. Yeah. And this is an opportunity to do this without burning fossil fuels, replacing things that need replacing without destroying the earth, using biology. And the idea of biology does it. In theory, if biology does something, we could get good enough to do it too. We're not at the level of biology yet, and who knows if we ever will be. But there are areas in which we make a pretty good stab at
it. The more you talk about this, the more it reminds me again and again of programming as a metaphor. I said hacking earlier for mRNA, but it feels that we now understand the cellular structure of life well enough that we can say, hey, here's a stalk of wheat. We know it's doing X, Y, Z. We wanted to do A, B, C. We can figure out how to, we understand how the DNA works. We can inject a gene right here, and it'll produce the thing that we want. And that seems obviously very powerful, because once the machines that we built, once we took them from, okay, we're mechanically changing them to, oh, wait, we can take one machine and program it to do a million different things. That was not just the Industrial Revolution, that was the electronic revolution, the software revolution, right? And so does that metaphor seem apt to you? Because I'm always wary of overusing computer metaphors because they tend to be overused.
Not to be overly complimentary, but it's the metaphor I use in this book, and I think it's completely accurate. I look at where we are in biology now as akin to the early days of the computer punch card revolution. After World War II, a computer took up a giant room in a building. It cost many millions of dollars, and only a few people could use it. Yeah. Now my watch has a computer in it that's more powerful than the one that sent astronauts to the moon. Yeah. And we are going to see that in biology. We are moving to a world where your kid is going to come home from 4th grade and say, look at the organism I designed, Daddy. And that's really cool and exciting. It also has some very scary elements attached to it, which we should probably talk about at some point.
Let's start talking about those now. I think we are moving into that space where, I mean, what you described, incredible innovation could be unleashed. Incredible benefits could be unleashed. You mentioned some of them. However, you know, humanity, when we get our hands on anything, we do good things with it and we do bad things with it. And, you know, our social structures tend to lead to the people who are in control of the technology and control of the innovation are specifically often doing things to benefit themselves rather than humanity at large. And the hopes at the beginning of any new tech, hey, when radio was invented, they thought everyone would be listening to classical music and taking college courses. And it became, soap operas and, we know where mass media went. So what are the concerns that you have specifically about this revolution that you're talking about?
Well, I mean, I do have a lot of concerns, and I should tell you, I teach a course with Kevin Esfelt at MIT called Safeguarding the Future. And a lot of it is about biology and a lot of it is about artificial intelligence, but it's these issues. And so what I mean with biology is it's great that your kid might be able to understand this and manipulate the basic elements of life. And it's amazing that scientists were able to download from blueprints on the internet something that allowed us to make a vaccine. But you don't have to be a genius to realize that if you can do incredible digital good, you can also do harm. And if I want to design a virus or alter a virus, and I live in Hudson, New York, and I want it manufactured in, name a place, Phoenix, Malaysia, Moscow, wherever, the internet will take care of that. And so now that we have biology moving at the speed of light at the same time when it's becoming more and more accessible, we need to think about guardrails, and we're not very good at doing that. You know, we have guardrails for nuclear weapons. They may not be perfect, but there are international treaties, there are agreed upon protocols. Nobody's going to go publish a recipe of how you make a nuclear weapon, or at least they're not going to be allowed to. I could publish a recipe to any virus you can possibly name. I can do it now. I can get it on the internet this second. If the New Yorker was crazy enough to let me, I could put it in any story and publish it. It would be immoral, but it wouldn't be illegal. And not only that, in the academic world, people want to guard the information they have and then publish it. That is how you get ahead. Those are the incentives. And somehow we understand that dangerous viruses should be put in special facilities. But their blueprints, let's just give them to everyone in the world. Now, 10 years ago, that wasn't as big a deal as it is now because there were fewer people who could make a virus or change a virus, and it was more expensive. But, just as the price of flat screen TVs used to be incredibly high and now they're not, the price of biological parts and computing keep falling. They fall really fast, and pretty soon this stuff is going to be accessible to lots of people. And it's something to worry about, for sure.
And so you mentioned, say, with that black-footed ferret example, that's being done with, I'm going to guess there's universities involved, there's, government agencies, the folks who are trying to conserve these species. There's a whole infrastructure. I can imagine all the wildlife biologists, in their bean boots and their like nice shirts, and they're doing a good job. And I would love to talk to these people. And I can trust that they're doing it in a good way. But as you say, once this is something you can just, program your genetic order in on AliExpress, right, and get somebody to ship you something, then not everybody is going to be that responsible. And so what are currently there are a lot of people who are really into biohacking and into trying to, they're injecting Crispr into their own veins and stuff like that.
Yeah, and some of them are my friends, to be honest.
Okay, you're getting freaky.
I have a weird crowd. I run with the weird crowd. This is something that I guess I kind of feel, this is simplistic, but the more powerful a technology gets and the more good it can do, the easier it can cause harm too. This is often talked about dual use technology, which I find a silly term because every technology is dual use. You can build a house with a hammer or crush someone's skull. But the thing that's changed with biology is it's digital now. It moves at the speed of light. So it's not like, gee, I could make a virus and then it might slip out and infect 47 people near my lab. It's, I could make a virus and I could email it to another bad guy and they could be making it in vats in the mountains of some place that I don't even know exists. And there are lots of ways that we can at least address this. And some people are starting to try, but it's not something that people think about. And as you've mentioned, I mean, it's really scary to think of the US Congress trying to figure out how to regulate the manipulation of viral particles.
Well, and it's hard to imagine them actually doing it. I mean, you mentioned AI, and AI is a pretty good example that this is a technology that is making massive, massive strides. It's suddenly spreading everywhere. You know, a model comes out and first it's secret and then you have to pay to use it. And then suddenly you can run it on your MacBook. And that, you know, that's happened over the course of the last 6 months to a year. And you've got these companies and all these thinkers who are saying over and over again, oh, we have to be careful about how we deploy this. We have to study it. The effects could be bad. Oh, we have to be so careful. And we have a lot of theatrical movements from those companies, like, you know, like OpenAI, which is the company that Microsoft invested all their money in. Well, it was founded as a nonprofit, and they write all these white papers about, oh, we have to be so good and ethical. And what do? They fire their ethicist teams. Both Google and Microsoft have done this. And then they just start releasing the shit and continue to make blog posts about how they're being responsible. But when you look at their actual actions, they're not responsible at all. And meanwhile, Congress, the government, they have no capability to even have a committee meeting about it on the time frame that the technology is advancing. So, I mean, I worry about talking about guardrails, but not having any societal means to create any.
You're right. I mean, I'll give you an example, and I hate to be an apologist. I think at Google, there are a bunch of people trying to do the right thing. So there's a company called DeepMind in London, and it's an AI company, and it's sort of famous for having been the first AI to defeat a player at Go, which is an infinitely impossible thing to do.
Yeah, that was a huge breakthrough when that happened. I remember that.
So I'm working on a piece about them now, and it's not about Go, but they did something else recently, which is they solved protein folding. Proteins fold in infinitely complicated ways. If you've ever seen pictures or like big giant balls of yarn or spaghetti. And in biology, they do this in a millisecond. Trillions of them all the time are folding and unfolding. But it's very hard to design a drug if you don't know how a protein is going to sit next to the other thing it's next to. It's not enough to just know what a protein is. So the protein folding problem was one that many people thought would never be solved. And what would happen is that people would spend 10 months and $50,000, $70,000, and they would use X-ray crystallography to figure out the dimensions of a protein. And you could do that. It would take a long time and it would be very expensive. And DeepMind decided, we're going to try this protein folding thing with AI. And people were a little skeptical. They solved it. They printed 300 million protein structures this year for free. And you know, they have other ways they want to make money. But the reason I'm telling you this story in part is because the person who runs that company is a brilliant man named Demis Hassabis. And I had a lot of conversations with him a few months ago that were theoretical. And I said, look, you guys want to do the right thing. I know that you have all these guardrails about not doing the wrong thing. But you're a private company, and private companies have to respond to markets. Yeah. And what are you going to do when someone releases something before you do?
Yep.
And Dema said it's a real problem. I think he thought it would be eventually a real problem. Now we're seeing that play out in the real world with GPT-4 and other
Yeah,
AI.
look at what Google did as soon as Microsoft's
Yeah.
trying to compete with Google. They rush their shitty AI-powered search engine to market. Now Google is suddenly changing their entire business model to keep up and throwing all the ethicists out the door.
You know, if you want to get a Google-like answer to something, you're better off asking ChatGPT. I mean, it will probably give you a quicker, better answer. The problem with these things, and it is a very significant problem, I mean, there are many, but one of them is they're trained on the internet.
Yeah.
And they're trained on billions and billions of pieces of information. And even if you think most of those things are accurate and true, they're not all accurate and true. And ChatGPT doesn't say, hey, by the way, this is a lie, but here's the thing that I've come up with. So the more and more we rely on AI to solve our problems, the more and more it's a concern that they get it right. And it's a really hard problem to solve, and the stakes are enormous. And again, it's one of those things where I can tell you so many things AI can solve and do for people.
Right.
But it can also do terrible things.
Well, I didn't mean for this to become the AI conversation, but I have it on the brain, and we all do now.
Yeah.
But let's bring this back to synthetic biology after we take one more really quick break. We'll be right back with more Michael Specter. Okay, we're back with Michael Specter. So we were just talking about, the pressure that capitalism and the desire to compete has on all these AI companies that causes them to, say the right things about ethics and then do the opposite, or to, bust over their own guardrails or to never set any guardrails up at all. So what are the risks of the same thing happening in synthetic biology? Like, what's something specific that you might worry about happening?
Well, I'm worried about accidents. I mean, forget about purposeful misuse of viral particles. Accidents happen all the time, like this ridiculous debate over the Wuhan lab leak theory.
Right.
It doesn't look like it was a lab leak, but you would have to not know very much about this research not to know that there are lab leaks all the time, and these things happen. And whether that virus came from a wet market or a lab, the virus doesn't care. It's just going to spread in the same way. So those are things that worry me. And if the more powerful we work on viruses, the more that worries me. I do want to point out that there are some cool solutions. They're not going to solve everything, but people are working on them. And one of them is, when you order DNA on the internet, there are certain sequences that ring alarm bells. Like, why do you want the sequence of a thing that looks like part of smallpox? Well, there can and should be some central registry that can sort of say, hey, we just saw what you ordered. Can we ask you why? And if they, maybe they're a lab at MIT that has a good reason. Yeah. Maybe they're a lab at MIT that doesn't have a good reason, or maybe they're like a teenager who thinks he's cool. But, we ought to be able to regulate that. The other thing, as we get to the point where we're able to print DNA out just on a DNA printer, which we can do, but it'll get easier and cheaper, you can put barcodes into DNA. You can watermark them. If you look at the US currency, it's actually not forged very well anymore. And that's because it's watermarked really well. Yeah. You can do the same thing with DNA, and we should. George Church, who's a famous geneticist at Harvard, has always said, synthetic biologists should have a license. Like, why is it you need a license for a gun or a license to drive, but you don't need a license to operate deadly viruses? Yeah. And then there's another thing that's a little futuristic. It's possible that there are wavelengths of ultraviolet light that you could put a light bulb in that would kill viruses and not harm any other living thing. Huh. This is new and it's not there yet. And a lot of people are going to say, oh, we don't believe you. Nobody's ready to do this. but a lot of people are ready to sort of look into it, because if you could actually do that, if I could say, wait a minute, I'm just going to put this light bulb in and then I know that this room won't have COVID or name another virus, that would be great. So there are solutions and people are trying to have them implemented, but it goes against the grain of society. And that's the problem. And I think one of the biggest problems is people don't understand this is coming so fast. And a lot of people, especially in my generation, they don't understand genetics and they really don't want to.
Yeah.
And they want the treatments. It's like with AI. Everyone's afraid of AI, but they don't mind their Netflix queue. They don't mind being able to take money out of their account if they happen to be in Italy. I mean, where do you think that comes from?
Yeah.
So again, there are good things and bad things, and we have to figure out a way for people to understand that, and we're not very good at it.
Yeah. One of the comparisons you made a few minutes ago really stuck with me, which is you compared it to nuclear weaponry, which is one of the most, and nuclear materials, nuclear energy as well, one of the most regulated substances and fields on the planet. But one of the reasons it's regulated that heavily is because it's the most powerful weapon on Earth. And the governments of the Earth want to have a monopoly on that, that they're, they're worried about, oh, what if people got their hands on it? But it's not like, hey, that wouldn't be safe if you did that. It's like, if anybody else has access to this, that's a problem for our entire country, and we've literally, look at Iran and it's like becomes a major issue of foreign policy, whether or not they have these. And the thing I want to say about that is that doesn't remove the risk, right? When the government has a monopoly on it, it means that it's only now going to be used for a certain purpose.
Well, it lowers the risk. It lowers the risk if 11 organizations or countries can do this as opposed to 11 million. And by the way, I would just like to say something that people will hate me for. Biology is a lot more powerful than nuclear weapons. If you drop the most powerful nuclear weapon on New York or Tokyo or Moscow, you'll kill 3-4 million people right off the bat. COVID has already killed way more than that. And that's not even a bad virus. I mean, we're talking about things that could be made.
We could have worse. Yeah.
Yeah. I mean, it's a bad virus, but it's, as historic pandemics go, its infectivity isn't that horrible.
It's no black plague. Yeah.
If bird flu, if avian influenza were this contagious, hundreds of millions of people would have died because it kills more than 50% of those it infects. It's just very hard to get it. But that can change. And the thing is about biology, if you have a good idea, you can email it to someone who can make it happen. And if you have a bad idea, you can email it to someone who can make it happen. And that's why I feel we need to focus more. And the problem, you're right, the problem with biology is we can't just have like 11 people. We can't turn the clock back and say the only people who can work with DNA are at fancy universities and labs. That's just not going to happen. So we have to at least make some attempt to regulate it. And I kind of feel it's a bit like gun control. Gun control doesn't solve not that we know what gun control is in this country, but if we had it, it wouldn't solve every problem, but it would probably reduce the risk and the opportunity. And I think that's the best we can hope for. And we're nowhere near that with biology.
I was just trying to make the point that, regulation in the case of nuclear weapons is not just about reducing the risk. It's about making sure that, only the most powerful people in the world want to make sure that only they have it. And the risk is reduced in some ways, but it's partially only reduced because we have a strategic stalemate. And we still have cases where you have countries like North Korea who are holding a gun to everybody else's head, metaphorically. And it's still something that there's a lot of fear about runaway catastrophe, right? India and Pakistan get into a shooting war and start dropping nuclear weapons on each other, and it like cascades very quickly. And so what you said in response to that is like, yeah, all that's true, except with biology, it's even worse.
Well,
And-
I have one chapter in this audiobook that focuses a lot on the original hearings on recombinant DNA technology, which took place in Cambridge in 1976. Harvard wanted to build a lab, and the mayor of Cambridge, who had this wonderful audio-ready Boston accent, went nuts and had a big hearing. They were famous hearings, and I got the archival tapes, and they're very insightful impression. At the time, they seemed ludicrous, but they're all questions that we ask now. And, I think we're seeing that this isn't just a problem of a madman. And what we need to do is figure out a way to at least put some guardrails on there. I don't think we can do what we do with nuclear weapons because it costs more to build them. But I think we can regulate things. And in fact, Cambridge actually does regulate this stuff pretty well. And when you make dangerous things, someone from the city council's on the board, and there is civic input.
Yeah.
That would help. I mean, nothing is a complete solution, but it would be nice to start moving towards understanding that it's a problem.
Why do you think, though, that it feels like there's comparatively little press about the precipice that we're currently on? Like, I think about, throughout the years I've been alive, things like test tube babies, Dolly the sheep, right? These were like huge, like Dolly the sheep was like a year-long news story. It's one of the biggest stories of that year. It was up there with Lorena Bobbitt in terms of how much people were talking about this. And GMOs, constant issue. Oh God, we're playing God. We're tinkering with life. And one of the strangest things about the COVID vaccine was that you didn't really hear that tinkering with life story. The people who are against the COVID vaccine didn't even understand it enough to know what was actually kind of scary about it, which was that we were learning to hack our own cells. They were worried about microchips and Bill Gates and shit that didn't make sense, not the real thing. And I'm not really hearing, like, GMOs, I know people are still upset about it, but it doesn't come up as often. CRISPR, there's nobody holding signs up saying, hey, protect us from CRISPR. Why do you think that is?
Well, I think it's because people don't understand what's happening. In that hearing I just mentioned, right after that, David Baltimore, who was sort of one of the founders of molecular biology and modern genetics, somebody asked him for a Nobel Prize interview, like why he thought there was so much anxiety at that hearing. And he said, it wasn't that long after World War II, and a lot of people were asking themselves a simple question: was there an atomic bomb in biology? And at the time, that seemed like a crazy thing to ask. It isn't a crazy thing to ask anymore, but I don't think people understand it. I covered Dolly. I was the Moscow bureau chief for the New York Times, but I had written about science, and my boss sent me to Scotland. And I wrote a huge story from the New York Times, which unfortunately lives on in the internet. And I made a big deal out of it. And it's cloning, and we're going to be cloning North Korean dictators. And we can clone some dogs now. And cloning has become very useful in agricultural animals. But we haven't cloned any humans, and we haven't even been able to clone any chimps. And so people, I think, freak out because they can envision cloning. It's very hard to envision when we talk about making a virus. People are like, what?
Yeah.
How can you do that? What does that mean?
Yeah. Well, here's the last question I'd like to ask you. We're talking about how some of those conservation points, about how we could, adjust the ferret a little bit. I think again about one thing I mentioned very briefly was the American chestnut, which is this, incredible, very important species of tree in American history that's almost wiped out because of a blight that we brought to it that almost wiped it out. There's been like a multi-decade effort to bring this tree back, I assume using some genetic technologies and others. And that would make such a huge difference. That would be a real positive because we could bring back entire ecosystems to the way they were, or at least have them be more flourishing, even if we're not turning the clock back. So these things are all really wonderful, but it sounds to me like our ability to edit nature is going to become so profound, and there's going to be so many cases that we want to use it, that it really makes me wonder, is this the end of nature, right? Is this we are, and I know that's such an such almost a dumb question to ask because we've already affected every single point on the globe. You can go to Antarctica and find microplastics and shit. I get all that.
Yeah.
But this is an ability to fundamentally change the world. And there's a certain, even when I go to the Griffith Park here in Los Angeles, there's still a certain weird blobbiness to it. We don't have control over everything. Shit is just still kind of happening, right? And if we're dramatically increasing our control over the world, does this turn, the nature that we have left into a gene edited park, eventually? Like does it really turn nature into nothing but yet another human technology? That's such a broad question, but what do you have to say about it?
It's an important question, but I think the answer is maybe down the line that'll be a problem. You have to understand, like, if you look at the human species, people originally were worried about we could edit people's genes with CRISPR and we could do terrible things to various ethnic groups.
Mm-hmm.
Well, first of all, a guy named Adolf Hitler proved that you don't need to edit genes to do that.
Yeah.
And secondly, to change the genetic basis of humanity, that's a many, 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 many generation thing. It would take many hundreds of years. Now, if it's a mosquito and it has a 7-day life cycle, yeah, you can really change the genetics of mosquitoes pretty rapidly. So there are a lot of animals that this isn't necessarily easily pertaining to. But it is true that we're just going to have to do a better job of, one thing we've never done, I've never heard of us doing this, is finding a technology and then never using it. We're going to have to start saying, are there some things we just don't want to use? Are there some places we just don't want to go? Because in the past, and with the atomic bomb, for instance, the answer is develop the technology and then worry about the shit afterwards. And that's just not going to be possible in a world where we are able to change the basic elements of life at the speed of light. Yeah. But I don't think that's happening tomorrow. I think we still have a little while left. And I don't want to be too dark because I do think it will bring a lot of benefits.
Yeah. Well, I can't think of an example in the past where humanity has ever not used a technology.
Me neither, and believe me, I've tried.
I'm not sure we have the power to do it, but I'm not the kind of person who says we need to leave this shit in the ground necessarily, because the benefits that you're talking about are enormous. The number of lives saved, right, and the amount of good that can be done with it. And at the very least, we need to be fucking aware that it's coming. So I really appreciate you for coming on the show to talk about it. The name of the audiobook, it's audiobook only, correct? What is it called? Yeah. Where can people get it?
It's called Higher Animals, Vaccines, Synthetic Biology, and the Future of Life, a nice minor topic. It's being published by Pushkin Industries, and you can get it on their website. You can get it at Audible. You can get it at Barnes & Noble. Wherever you get audiobooks, you'll be able to get it starting March 28th, but you could pre-order it.
I'm going to listen to this because I saw it's about 4 hours long, which is like a perfect length for an audiobook. This is such a fascinating topic. I appreciate it. It was wonderful having you, Michael. I hope you come back sometime.
Oh, I'd love to. And I will tell my colleagues to rapidly get on your show.
Yes. All right. Thank you so much.
Thanks, Adam.
Well, thank you so much to Michael Specter for coming on the show. If you loved that conversation as much as I did, I hope you will consider supporting our show on Patreon. I want to thank everyone who supports the show at the $15 a month level, and we're going to read out some recent names. We've got Mick Pwoninator, great name to start with, Ashley Molina Diaz, Ask, Ghost, Francisco Ojeda, Dark Avenger, and yet another Mike. Thank you to all of you for supporting the show. If you want to join them, head to patreon.com/Adam Conover. And once again, head to adamconover.net to get tickets to my live shows all around the country. I want to thank our producer, Sam Roudman, and our engineer, Kyle McGraw, and the fine folks at Falcon Northwest who built me the incredible custom gaming PC that I record every episode of the show on. You can find me online at adamconover.net or at Adam Conover, wherever you get your social media. Thank you so much for listening, and we'll see you next time on Factually.
Starburns Audio, a podcast network.